Thank you for attending the session today. Today is not a typical webinar that we would give, but it is going to be very educational. It's actually a product launch announcement. So we are announcing today the official availability. We're no longer in user beta testing. We are officially launching our Bowtie-Q product for doing quantitative bow tie analysis. So what we're talking about is probably the most sophisticated piece of bow tie analysis software, whereas some other software applications just draw a pretty picture for you. As a matter of fact, the most common way to do bow tie diagrams I hear is in Visio or PowerPoint. But no. We're fully object-oriented quantitative analysis. All of the most sophisticated features are going to be available, and we are launching today. So I'm going to talk about the product itself, and I'm going to start out with a little bit of discussion on the overall bow tie analysis process, its history, why you would do it, and then I will get into a description of the actual software itself. Now, so I'm going to start with some PowerPoint slides, then I'm going to move over and provide a discussion of the software itself. So let me go ahead and share my screen. So what you're looking at here is the Bow Tie Analysis Theory and Fundamentals training course. So this training course is going to be available for live presentation to groups if you choose to do that. And it is also going to be included as one of the many training classes that are available inside the Connexus Process Safety Training Center that's part of the Connexus Integrated Safety Suite. So let's talk about bow tie analysis. So I'm going to skip over the objectives because we're not going to cover all these objectives. Actually, what we're going to talk about today is the first two bullet items, is understanding the fundamentals of bow tie analysis and how do we apply bow tie analysis in risk identification and control. I'm going to go through section 1 and I'm going to go through section 2. All very briefly, not in the level of detail that I will go through it in the full training class. So section 1, Introduction to Bow Tie Diagrams. So bow tie diagrams, I'm going to talk about how bow tie diagrams fit into the overall risk management process, a little bit of history and evolution of bow tie analysis, and specifically what is going on in the Connexus version of bow tie diagrams and how that's going to get integrated into the software suite. And I'll talk about specific Bowtie-Q information because it is, again, on the way more sophisticated side than some of the other bow tie applications that are out there. Ultimately, the big benefit of doing bow tie diagrams is being able to visualize risk. So instead of your risk being a bunch of numbers on a spreadsheet that many people have difficulty processing, we're going to provide a clear visual representation of a hazardous scenario, including what are the causes, what are the consequences of the hazardous events. So we're going to bridge the gap between a qualitative visualization and a fully quantitative analysis. So this is kind of furthering the overall Connexus message of a unified process hazards analysis, where you're going to be able to go fully quantitative through qualitative visualization, all in one framework. Now, who uses bow tie diagrams? Everyone can use bow tie diagrams, from the chemical process industries, aerospace, pharmaceuticals. As a matter of fact, even though most of you are in the process industries, the application that I'm going to be talking about in my example is actually going to come from data centers. So I'm going to talk about bow tie diagrams for those data centers that Google and Amazon and Microsoft are popping up all over the place. So lots of different applications. When you look at a bow tie diagram, it is going to include several things. So there are going to be top events. So the bow tie knot, and that's the bow tie knot right there, is a top event. It's a critical incident that occurs when the control is lost. But in and of itself, it is not a consequence. We're going to talk about threats. These are factors that could cause the top event. We're going to talk a little bit about terminology. Again, back to that concept of unified hazard analysis. A threat is a bow tie diagram term, but if you were doing a LOPA, you would call this an initiating event. If you were doing a HAZOP, you would call it a cause. But it's all the same thing. So what are the things that can result in the top event if they occur? Consequences are the potential outcomes. And the beauty of the bow tie diagram, as opposed to a HAZOP or a LOPA, is that one visual framework can show you multiple different consequences simultaneously. We'll talk about barriers, which in the language of HAZOP would be safeguards, in the language of LOPA would be independent protection layers. And the other neat trick that the bow tie diagram does that's more sophisticated even than LOPA is that you can distinguish between preventive barriers on the left-hand side, which are things that prevent that loss of containment event. So this top event in the chemical process industries is typically going to be your loss of containment. And we also have the ability to handle mitigative barriers, which are things that will not prevent the loss of containment, but make the consequence smaller given that the loss of containment has occurred. So if you have a containment dike around your storage tank that is designed to contain the spread of material that gets spilled out of a tank, that's not preventive. It didn't prevent the spill. It's mitigative. It makes the consequences smaller. And then the other thing that bow tie diagrams do, which is especially important in the later design phases and the operational phases, is it allows you to discuss and document degradation factors and degradation controls. So those things that will prevent your barrier from operating over time, and the tasks and the equipment that we use to prevent that degradation. So a lot more detail than any of your previous PHA studies, whether that be a HAZOP or a LOPA. All right. So bow tie analysis in the risk management process. Bow tie analysis helps to identify hazards to some degree. Honestly, by the time you get to a bow tie diagram, you've already done all your identification. Bow tie diagrams usually happen after a HAZOP and after a LOPA. It's the next step to help in visualization. So, but it will help you to catch any mistakes that you made. It aids in the assessment of severity by really clearly visually representing the risk. It's going to highlight all the barriers and what type of barriers they are, helping you establish performance standards for those pieces of equipment. And it's going to be tightly integrated with other tools such as HAZOP and LOPA and equipment design and maintenance systems, especially if you're using KISS. So if you're using KISS, you don't lose anything from one stage to the next. You're going to be able to do your HAZOP, take that information over into a LOPA, take that information and carry it into the bow tie diagram. This all allows for continuous improvement and efficiency. So bow tie is part of the KISS suite. It's going to support your overall risk identification and risk management processes. And the bow tie analysis part of the software is going to help you to do that visualization, but it also has some really sophisticated quantitative features that are more advanced even than what is available in the open PHA LOPA, specifically the ability to handle multiple consequences simultaneously. So we're able to link to other assessments, and we're able to link to other design tasks that are performed in the KISS tool set. So where did bowtie analysis come from? Actually, bowtie started appearing in the early 1970s in the oil and gas industry. So oil and gas, one of those things where massive failures are possible, massive consequences are possible, simply due to the scale of what we're doing and the flammable and toxic nature of the materials that we're working with. So bowtie was used to manage catastrophic risks. So right there's a key that says we're probably not going to want to run a bowtie diagram for every HAZOP scenario. We don't want bowtie analysis replacing HAZOPs because they just take too long to develop. So they are originated from the desire to integrate a fault tree analysis, which is the left side of the bowtie, with an event tree analysis, which is the right side of the bowtie, into a single coherent visualization. At the beginning, we were kind of doing things really qualitatively just to get a feel for it. So first documented use was Shell in the 1970s for hazard identification and risk mitigation. And the structure praised right out of the gate for conceptual simplicity and visual appeal. So early application in high-risk industries, we started off with oil and gas, and we were looking at blowouts, explosions, oil spills. And from there, it actually quickly became a key tool for complying with safety regulations. Now, a lot of you in Australia, a lot of you in Europe, your regulators are demanding that you present to them bowtie diagrams of the major accident scenarios, and they use those bowtie diagrams as a map for how they're going to inspect your plant, looking at all the barriers, making sure that all the barriers are in service and have their associated testing records. But then it was quickly adopted by other industries. Aviation is using bowties for flight safety, air traffic control risk. The nuclear sector is looking at it for reactor operation and material handling. So through the decades, in the 70s, early initial development, conceptualizing risk scenarios. We get into the 1980s, and we're starting to use it on a regular basis as part of the formal safety protocols instead of a one-off thing. Going into the 90s, more formalization and standardization and more use across multiple different industries. Once we get into the 2000s, we start integrating with digital tools to make the development more efficient. Of course, the most common digital tool would be PowerPoint, where we're just drawing a picture instead of actually using it. 2010s, again, more industries. We started going into healthcare, pharmaceuticals, logistics, trucking companies using bowtie diagrams to assess the probability that loads aren't going to make it to their destinations. And now we are adding more and more advanced features into the process. We're using cloud-based software. We're integrating our data in real time with other systems. We're using more advanced graphics and quantifying things. All right, so the role of technology in bowtie evolution, the technology in bowtie evolution is one of the stories of the Connexus Integrated Safety Suite. We have the ability to digitalize the bowtie diagrams, breaking it into its fundamental data structure instead of making it just a pretty picture. This is going to allow us to integrate with other risk management software. So you don't need to pull out PowerPoint and start drawing a picture when you can export out of OpenPHA and have a bowtie diagram built for you automatically. Ultimately, we're going to be able to use this tool for real-time monitoring and data analytics. So KISS, as you know, has a lot of application programming interfaces where we can pull data in and out from things like other maintenance management systems and online historians of process information and make all that available. We're now able to do advanced quantitative analysis inside the Bowtie diagram instead of just a pretty picture, and then more collaboration and more accessibility in that cloud-based framework. Where are we going in the future? The sky's the limit. Predictive analytics, real-time monitoring, a stronger focus on human factors, and maybe even having a little bit of artificial intelligence to help you develop and interpret what these Bowtie diagrams are telling you. A lot of automation that's currently built into KISS, but it's getting stronger every day. Scalability, customization, and we are going to keep going into new industries because it's such a valuable tool. All right, so that's kind of an introduction to Bowtie analysis. Now let's talk about a little bit more of where the rubber meets the road, a little bit more detail on actually what we're trying to accomplish and how we're going to accomplish that. So we're going to talk about how to actually build a Bowtie diagram. We're going to talk about that terminology again and kind of try to roll it back to that unified hazard assessment approach. And we're going to understand the different barriers. And finally, we're going to kind of end off with a data center example. All right, so the key components of the Bowtie diagram are shown on this figure here. I am not going to belabor this too much on this screen because we're going to do a deep dive into all these components. But basically, we have the Bowtie knot. Whoa. Sorry about that. The Bowtie knot, which is the top event. Our causes or threats. On the left-hand side, there can be many of them. And on the left-hand side, there are preventive barriers that are on a threat-by-threat basis. Barriers can have degradation factors and degradation controls. So things that make the barrier fail, and how do we manage that barrier to ensure that it doesn't fail, or if it does fail, it's repaired very quickly. On the right-hand side, we're going to have potentially multiple different consequences, and also each consequence can have one or more mitigation barriers that again, they don't prevent the top event from occurring, but if the top event occurs, they reduce the likelihood of any potential consequence outcome. So they're going to make the consequences smaller as opposed to preventing the consequences. Okay. So let's just start out with some beginning terminology. Hazards. Hazard is what we're trying to prevent. It's the source of potential harm or risk. It can be physical, chemical, environmental, operational, depending on what your paradigm is. So the hazard is the potential source of harm, where the top event is the point in time where you actually lose control over the hazard and expose that hazard to the assets, to people, to the environment, to your neighbors. So in the process industries, that top event is going to be your loss of containment. So if I were looking at a storage tank, the second that I overfill from that storage tank, that's my top event, that's my loss of containment. So critical point where control is lost, and when this occurs, the threat materializes because the preventive barriers fail. So this is the moment in time where you lost control of the hazard. And then the relationship that exists between hazards and top events is that the hazard is always there. If I have a toxic chemical, I have a hazard. But as long as it's controlled, I don't have a top event. The top event is the loss of control over that hazard, and that top event is going to be the knot in my bow tie diagram. Now, for each top event, we're going to have one or more threats. So a threat is an event, an action, or a condition that can cause the top event to occur. Okay, and each top event is possible. It is possible to have multiple different causes of that top event. So these threats, and again, using that terminology, threat is the official bow tie name, cause is the HAZOP name, initiating event is the LOPA name, but it's all the same thing. They can be operational, they can be environmental, they can be procedural. So a lot of different things can cause the top event to occur. What is the role of threats in bow tie diagrams? Well, we're going to stick them all on the left-hand side and connect them to the top event. So these are the causes, and we're going to want to then look at the barriers that are going to prevent that cause from resulting in the top event. Now, on the far right-hand side, we are going to have consequences. So a consequence is the ultimate loss of the asset. It's the degree of harm or loss from control, loss of control of the hazard. So if I have a storage tank overfill, I can have a fire, and that fire can result in potential injuries. That's the harm from the loss of control event. And in Bowtie-Q, you're actually going to be able to set consequence categories the same as you would in a HAZOP or a LOPA. And most of the time, these are going to just get carried over from the HAZOP or LOPA that you did directly into this framework. So we're going to make a list of consequences. And again, consequences can be of multiple different dimensions. So there could be a safety impact, an environmental impact, asset impact. All of the dimensions of consequence that you have in OpenPHA, you're also going to have in Bowtie-Q. So what is the role of consequences? We're going to put them on the right-hand side. There's going to be at least one, but there could be an infinite number. So as many different types of consequences as makes sense for the scenario. So loss of control can result in many different consequences, and looking at the magnitude of those consequences and all of your barriers are going to help you set up your risk prioritization strategy. Now, we have barriers. Barriers are going to be either preventive or mitigative. So what is a barrier? It's a control, a risk control that will either prevent the top event from occurring. Those are our preventive barriers. They're going to be on the left-hand side. They're going to include things like high-level interlock, operator intervention based on high-level alarm. Those are preventive. If they function properly, the overfill will never happen. Okay, so those are preventive barriers designed to prevent the top event from occurring. Mitigated barriers, on the other hand, reduce the consequence. So if I overfill a storage tank and there's a containment dike, the pool area is smaller, so the magnitude of consequence is smaller than if there were no containment dike, and that spill would be much larger. So minimize the consequences. So fire suppression systems, evacuation procedures, containment dikes, emergency scrubber systems are all examples of mitigative barriers. Okay, so barriers act as safeguards to protect against the risks, and we need to document them. Now, this is what's new. So if you're familiar with HAZOP, you're familiar with LOPA, but you're not familiar with bow tie diagrams, then you've probably never been exposed to the concept of degradation factors and degradation controls. So degradation factors are conditions that reduce the effectiveness of barriers over time, things that can compromise a barrier. So if I look at a high-level interlock on a safety instrumented system, what are the things that can prevent that high-level interlock from working? Well, one of the things that can prevent that high-level interlock from working is somebody might have put it into bypass. Okay, so if the device is in bypass, then it's not going to operate when you need it to. So that's a degradation factor. And for each degradation factor, you can have multiple degradation controls. So you might have a bypass management program that restricts who can implement a bypass, how they perform the bypass. You might have a system to put together a worksheet that needs to be approved before you can put something into bypass. And you might also have another program to, on a regular basis, check what is in bypass, ensure that it still needs to be in bypass, and remove it from bypass if it is no longer necessary. So what you're seeing here is you start drilling down deeper into what can go wrong and how you're going to control it in that bow tie diagram. So we're continuously expanding. We started with the HAZOP, where just the fact that we have an interlock was documented. Then we went into LOPA and we set performance targets and looked at the detailed attributes of the interlock. Now that we get into bow tie diagrams, we're going to start drilling down even deeper into what can go wrong and how am I controlling it. So those are degradation factors and degradation controls. Now, when you're developing bow tie diagrams, what can go wrong? Well, number one, I've got incomplete knowledge of my scenario. I didn't list out all the causes. I didn't list out all the consequences. I can oversimplify what the barriers are, meaning that I don't account for everything, or maybe you account for things that won't actually work. Hopefully by the time you've gone through your LOPA process, you would have determined whether or not the barrier is actually creditable. But that's another potential source of failure. Failure to account for degradation factors. There are so many incidents in industry where ultimately the barriers were in place, but they failed because they were put into bypass, they weren't maintained, etc. Misplacing, mislabeling barriers, so calling a mitigative barrier preventive and so on. Lack of quantification. Now, a lot of times all you want is a picture, but putting numbers on that bow tie diagram is something that started in layer of protection analysis and can get carried through the overall process. And finally, failure to validate your bow tie diagram. So not going through that process of making sure that what's on paper matches the policies, procedures, and equipment of what's actually out in the field. Okay, so a step-by-step guide to building a bow tie diagram. Number one is identify the hazard. Number two would be to determine the top event. So I'm going to have a top event, and honestly, again, these are coming out of your PHAs. We're going to identify threats, also known as causes or initiating events. So again, a lot of this is carried over from previous studies. We're going to identify the consequences. Now, this is where things get a little bit different. HAZOPs usually do either one cause-consequence pair, or there will be a cause with many consequences. Traditional LOPA has one consequence with multiple different causes. Well, by the time we get to bow tie diagram, we've looped everything together to say there is a top event, and it can be caused by multiple different things, and the consequences, there could be multiple different consequence scenarios depending on what mitigative barriers activate. So what are all of the consequences? And then we'll put in our safeguards, our independent protection layers, or in the language of bow tie, our barriers, and we'll put them on the left side if they prevent the top event, the right side if they reduce the consequences. Then we are now going beyond what was done in the HAZOP and the LOPA phase by talking about what the degradation factors are and documenting what the degradation controls are. And then finally, we will validate the diagram against the actual operation of the plant to make sure that our bow tie diagram is accurate. Once we get to this stage, we have a tool that we're going to use for the rest of the safety life cycle for management of change, operation, education, and communicating with stakeholders like regulators who will then use this as a roadmap for how they do their inspections. Okay, so now we're going to do a quick example, and we are going to look at our building loss of power. So let's say we have a data center that's being built. And here in Columbus, Ohio, I know of at least 3 different data centers that are currently in construction within a 10-mile radius of Connexus. So a lot of this is going on right now. So we're building a data center that's going to house our company's databases and cloud computing infrastructure. So what we're going to do is we're going to consider what are some hazards and make sure that we are managing the risk of those hazards. So a hazard for a data center is that we lost our electrical supply. So if we lose our electrical supply and we're a critical building, so whether that's a data center or a hospital or an office building, losing your electrical supply is a bad thing. And the loss of electrical supply, we can convert that into a top event, which is the complete loss of electrical supply to the building. So when we enter the bow tie diagram, the first thing that's going to show up on the page is going to be our top event, and we will give that top event a name and a description, as you see in the worksheet here, name and description. Obviously, we're also going to be able to change colors and provide notes, all kinds of other good things related to that. So there's a data structure that's going to be underpinning this. After you determine what the top event is, you're going to ask yourself, what are all of the threats? What are all of the things that are going to be capable of causing a data center failure, data center power supply failure? So if I want to add a new threat, I simply click on the plus button. It's going to generate a new item, and you give the threat a name and a description, but there's a lot more stuff under the hood. So if I press the expand button right there, I'm going to see all of the attributes. If I hit the edit button, I'm going to get that pop-up window that shows me everything that's on the screen. Okay, so what we determined for our data center is that if the electrical grid fails, I'm not going to get an electrical supply. Also, if the transformers or switchgear that's in the building fails, I'm also going to lose my electrical power supply. Another cause is human error. So if the operators or technicians that are working on the internal infrastructure accidentally shut something off, I'm going to lose my power supply. And then finally, another thing that we're worried about here in Ohio at this time of year is natural disasters. We get our fair share of tornadoes here in Ohio, so it's something that we need to think about when we're designing any infrastructure. So those are the causes that we've determined, and again, we can do a lot of detail in how far we quantify these things. After we determine what the threats are, we're going to want to list out what all of the consequences are, not just what we would do in a LOPA, which would be, well, what is the worst credible consequence, and just kind of pin everything on that. We're not doing that here. We're going to list out all the different consequences. So once again, you've got the name and you've got the description, but there's a lot more potential information under the hood that when we get into the actual product demo, I will talk about that in a little bit more detail. So we decided that, okay, the consequences are we're going to get a disruption of operations. So our computer systems are going to be unavailable. We're going to get financial losses because, well, maybe we're not meeting service agreements. We promised 99% uptime and we're not making it, so we need to pay our customers back. And then also lost reputation. If we get a reputation as the people whose data centers go down all the time, no one's going to want to buy from us. So these are all the different consequences that we list out. So at this point, we've got our threats, we've got our consequences, we've got our top events. Now we're going to start putting in barriers. And we're going to start on the left-hand side and put in the preventive barriers. So for instance, for grid failure, I've got two preventive barriers. So I might have an uninterruptible power supply system, so a bank of batteries and inverters that is going to supply short-term power immediately to prevent my system from going down. Now, I might also have a redundant power supply. So I might have backup diesel generators that I'm going to use to generate electricity to supply power to recharge the uninterruptible power supply and feed the system in general. So what you'll notice here is that each threat has its own set of as many as you want. You can put in an infinite number of preventive barriers. And the preventive barriers are tied to specific threats. So this uninterruptible power supply is a barrier against grid failure, but it's not a barrier against human failure. There are no barriers against human failure. If the technician flips the power off, the power is off. So the number of barriers and the specific barriers is going to vary depending on what your threat is. And also you have the ability to use the same barrier in multiple locations. So you don't need to define them. So if, for instance, an uninterruptible power supply was a barrier against this threat, I can simply pull it out of the database and say that this barrier applies to this threat also. So very powerful, very efficient kind of a data structure that we're using that underpins the development of the diagram. So the other thing that we're going to have is the mitigative barriers. So emergency power procedures, backup generators. So this is something that, you know, a backup generator might not be able to provide you power until 10-15 minutes after you lost power, depending on what the type of backup generator is. And you see here that this backup generator is repeated for all of the consequences. But in the database, there's only one entry. So if I make a change here, it's going to cascade to all of the linked instances of that barrier. Okay, so preventive barriers prevent the loss of containment or prevent the top event from occurring. Mitigative barriers make the consequence smaller. So if the mitigative barrier works, instead of a 1-day disruption or a 2-day disruption of operations, I might only have a 15-minute disruption of operations. Now, degradation factors and degradation controls is something that might be new to some of you because it's not part of that standard HAZOP-LOPA process that you're used to. And this is exceedingly valuable because you're kind of doing a bit of a failure modes and effects analysis inside this framework to help you understand what PM tasks you should be implementing. So for your barriers, you will list out, well, what are all of the failure modes that are possible? I'm sorry, those are the controls. These are the failure modes. So just aging infrastructure due to wear and tear. And then, insufficient fuel available for the backup generator. Those are things that will prevent those barriers from working. So these degradation controls, I can also kind of, in language that you might be more familiar with, these are, if you will, the failure modes of those equipment items. And then these degradation controls are your, kind of going back to terminology that you might be more familiar with. These are going to be your PMs, your preventive maintenance tasks. Now, that's being a little bit too narrow. Degradation controls is going to involve a whole lot more than just PM tasks. It's going to be inspections, it's going to be policies, it's going to be procedures, and so on. So looking at that first degradation control, you say, well, aging infrastructure is a potential degradation factor that can prevent the backup generators from working. So how do I overcome that? Well, I'm going to do regular inspections to make sure that the devices actually work. So, and then also, wouldn't it be nice if we could take this and link it back in to a computerized maintenance management system to actually determine whether or not this is actually being done. The options are limitless for the future directions that we're looking at here. All right, so that was section 2 out of 8 sections in the Bowtie Theories and Fundamentals training class that is available today for live presentation at your site or through Teams meeting, and it will be uploaded into the Connexus Process Safety Training Center within the next few weeks. Okay, so that's kind of the overview. Let's get out of the presentation and actually get into the software. So I am going into my web browser because, as everybody knows, KISS is cloud-based and it's accessed through your web browser. So I'm going to go to kiss.connexus.com, hit the enter button. I'm already at 150% magnification so that human eyes are able to see what's on the screen. I'm going to take advantage of the single sign-in capabilities of KISS to just click on sign in with Microsoft. I'm logged into Office 365, so it knows that I'm legit and it lets me right in. What I'm going to do now is I'm going to go into a folder called EMM Samples, which is where I do a lot of my training class development. So when I'm developing training classes and doing online presentations, webinars, all those conferences, this is where I do my work. So what we looked at previously was the data center loss of power. So I'm going to go ahead and bring up the data center loss of power. So here we are in Bowtie-Q. When you jump in and land in Bowtie-Q, you're going to get general information. So what is the study, project numbers, notes, and so on. You're going to have kind of how many Bowtie diagrams are in here, how many causes, consequences, safeguards do you have. And then down at the bottom, we have information that allows you to do revision tracking and also document recommendations. So everything in the KISS framework is capable of generating recommendations, and that all is going to be dashboardable. Dashboardable, is that a word? Yeah, I guess. In the overall facility dashboard. So you could drill down into whatever level of your hierarchy and look at those recommendations, and those recommendations will include things out of Bowtie-Q. Okay, so this is the overview page. The next thing we're going to do is go into the bow tie pages. So on the bow tie pages, on the left-hand side, you're going to see your selector area, your list area, list view. And on the right-hand side, you're going to see the graphic of your bow tie diagram. If you don't want to see the list view, you can close it and make your screen a little bit bigger. You can click here to open it back up. Now you'll see that I only have one bow tie diagram, which is called bow tie 1. But I could create another bow tie diagram, and let's call it bow tie 2, just to keep some consistency here. And when I do that, you'll see that in the same study, I can have multiple different bow tie diagrams. So I'm going to come back to bow tie 2 a little bit later when I'm showing you the structure of how things work. So bow tie 1, bow tie 2, all in the same study. And here you're also going to see a list of the safeguards that are available in the study. You can double click on them to dive into the data structure and look at them in a little bit more detail. Okay, so this is kind of the main view where you're going to be doing your work. If I look at the bow tie diagram workspace, you'll see that I can do several things. I can make a compact view, which is a little bit easier to see. You're going to get a lot more stuff on the screen. This is something you might want to do when you're printing things out. And in the compact view, you're only going to see names and descriptions. So the amount of information that's available is limited. Whereas when we go into the larger view, we're going to have a lot more information, and we're going to have a lot more tools available to us. Okay, kind of going along the view, when you click here, you'll get a list of all of the causes that are available in every bow tie diagram. So you see here that natural disasters is used in bow tie 1, but cause 1 is used in bow tie 2. In the middle here, you're going to have a list of all of the safeguards, along with all of the places that those safeguards are used, and also the ability to drill down into those safeguards in a little more detail. Next up is going to be a list of all of the consequences and the places that they're used in terms of which bow tie diagram. Now, something that most other bow tie analysis software does not give you is going to be the risk matrix. Now, many of you are probably OpenPHA users, so you're going, huh, that looks mighty familiar. Yes, it's exactly the same code base sitting in Bowtie-Q as is sitting in OpenPHA, which should probably get you thinking that these Connexus guys are probably using a common code base to do all the tasks so that I can share data across applications and minimize my workflow. That's exactly what we're doing. As a matter of fact, here there's a save button. You can expand and contract. You can look at your likelihood categories, your consequence categories, your risk rankings. All this is going to be very similar, very familiar to, not similar, identical to what you're seeing in OpenPHA. So that's how you develop your risk criteria, which is going to become important to you. And then over here, we have a study settings tab. So those of you that are Connexus aficionados that have been with us for the long haul, you know that we are proponents of customization and flexibility in what you see. But the underlying data structure is always going to be fixed and is always going to be consistent, so that we can do data export, we can do APIs, we can do data migrations, we can do dashboarding. That all relies on a standard data structure. But you can decide whether or not you want to see things. So in these study settings, you see that everything is unchecked. I'm not showing you anything, and that's because some users of the software simply want a visualization of risk, so they don't show you any of the details. But what if I want to see the details? So for a cause or a threat, maybe I want to know what type it is. Maybe I want instrument tags. Maybe I want to put a frequency on it. Maybe I want to put a mitigated frequency on it. We'll come back to that later. And then for those of you in the cybersecurity space that are doing security PHA reviews, you can do that in Bowtie-Q, because all of the hackable, non-hackable logic and infrastructure is built into Bowtie-Q the same way that it's built into OpenPHA. So let me jump out of here and go into a more detailed Bowtie diagram that's probably going to be something that's more familiar to the process industry people that are in the that most of you out in the audience are. So now I'm doing a different type of scenario in the process industry. So where I'm going to overfill a storage tank and I'm going to potentially lose containment. So now when I open up the safeguard details, I'm going to get all the information about the safeguard. When I open up the edit for the cause, I'm going to get a wider variety. So in this case, when I go back to the study settings, you'll see that the cause is going to show type, tag, frequency, mitigated frequency, but it's not showing the hackable, which is going to be kind of more reserved for your security PHA reviews that you would do for a cybersecurity study. So now I'm showing everything other than the cause field. And this information is available when you double click on it, when you hit the edit button, but also when you hit the expand button here. Now it's going to allow you to show those attributes actually on the Bowtie diagram. So if I'm in here and I want to know what frequency is associated with this initiating event, I can see here that it's 0.1 per year. Okay, so that's the causes. And similarly, for the protection layers, for the barriers, we can drive down and do a lot more detail. So assign SIL targets, whether or not we've achieved the SIL targets. Is this safeguard an independent protection layer? Is it a safeguard? And these kind of tie back to the HAZOP and LOPA. A lot more information. And as you can see, we're starting to see some numbers show up. Now, before I delve into the numbers, let me go through a little bit more of the mechanics. So if let me go back here, create a new Bowtie diagram. Let's call it Bowtie-2. Hit insert. I'm going to have an empty shell. And in this empty shell, I'm going to define what the top event is. So here, let's say that the top event is a hydrocracker runaway reaction. I'm just going to copy a little bit here. Resulting in loss of containment of the reactor system. And I could put in some notes, and you know what, let's go ahead and make this red so everybody understands how scary this actually is. Now, for the hydrocracker runaway reaction, what are some of the causes of a runaway reaction? I already have one cause, so I'm going to say that feed pump failure is going to be a cause of runaway reaction. No need to belabor a description here. Actually, let me step back here. So I'm going to actually, it might make more sense to put a tag number in here and say pump 101, or you could put that tag number in here however you want. This cause type could cascade over from OpenPHA, or you could give it a cause type like rotating equipment failure. And we can assign it a frequency of 0.1 per year. And let's say that, okay, for my rotating equipment failures, I'm going to make those all purple and cascade along. So now I've got my feed pump failure. And let's say that there's more than one cause. So if I have more causes, I simply click the Add Cause button. And now I'm going to get a new cause. And here, I'm going to say that the cause title is Feed Composition Change. So those of you that are in the business know that if you change your feed composition to include more olefins, more double bonds, more alkenes, if you've more recently graduated from college, that's going to make the reaction a little bit more violent and potentially cause you to run away. And then I'll kind of elaborate in a little bit more detail. Feed composition change resulting in excess reaction and temperature increase. Very good. The cause type, I'm just going to say NA, and for instrument tags, I'm going to say NA. Actually, I'll just say feed composition here if I wanted to do a cause type. Usually the cause type is going to be tagged to a type of initiating event in your LOPA procedure, honestly. And let's say the frequency here is going to be, once per year. You've got the chance of changing from one type of crude to another type of crude that's a little bit hotter. Okay, and then, you know, this is kind of an oddball. I'm going to make this this guy yellow to just kind of distinguish between things. Okay, so that's how you do this. You're going to add as many causes as you want and kind of carry on. Next thing you're going to do is you're going to put in your consequences. So the worst consequence that I'm going to be concerned about would be a run-away reaction with jet fire. So I'm going to expand on that a little bit more and say reactor run away resulting in loss of containment in reactor outlet piping. Release is expected to auto ignite and develop into a large jet fire. So that's generally what we expect to happen in this scenario. So then the next thing we're going to do is select a severity. Now, right now it's telling me I only have an environmental severity because that's what we were worried about in the diesel tank overview. I'm going to say that the consequence is very high. And let's go ahead and make this orange just because I want to have a whole variety of different colors. Okay, so now I've developed what my consequences are, and as you can see, I can give it a risk ranking out of my consequence categories and my risk matrix. Again, if I wanted to give it more than just a environmental consequence, I would go over here to consequence field visibility and say I also want to see a safety consequence. I'm going to need to change my safety severity here to a very high, and actually let's change my environmental severity to medium. So each category can have a different ranking. And I'm going to hit update. And now when I expand, you'll see both of those consequences. And also looky here, we've got these red dots by the consequence type. When you see a red dot on a consequence, that tells me this design does not achieve tolerable risk. Why does it not achieve tolerable risk? Well, my safety severity is very high, which means that the target maximum event likelihood is 1 times 10 to the minus 5. Where did that come from? Well, that came from our risk tolerance criteria. So if I go to consequence categories and I look at safety, for a very high consequence, its TMEL is 1E minus 5. All exactly the same as you would do if you were in open PHA. So now, sorry, wrong Bowtie diagram. So 1 times 10 to the minus 5 is what my target is, but once per year is the current frequency. So if my target is 1E minus 5 or less than 1E minus 5, and my estimated is 1, my mitigated event likelihood is 1, I don't achieve my my tolerable level of risk. So what I'm going to need to do is I'm going to need to start putting in some safeguards. So in terms of putting in safeguards, we added causes here, we added consequences, and I'm just going to put in other consequence here, and put in very low for safety and medium for environmental. And what the hell, let's change that color. Most of the time, everything is in Connexus blue when you get something from Connexus, but I feel the need to put in a lot of different colors today. So this is how you would add in a second consequence, and you'll see that the consequences for the rankings for the second consequence are different from from the first consequence, but I'm still red lighted because in both cases I have not achieved my tolerable level of risk. So let's put in some safeguards. So we have preventive safeguards and mitigative safeguards. If I want to put in a preventive safeguard, let's say a preventive safeguard against feed composition change, I would click here to add a safeguard. And the first thing it's going to ask me is, do you want to add a new safeguard, or do you want to link to an existing safeguard? I'm going to say add new, because let's say I haven't documented this safeguard yet. So this safeguard I'm going to say is TZC 425. So temperature safety instrumented system controller 425, and the description of this interlock is going to be high reactor temperature shutdown. It is a safety instrumented function. The tag is going to be TZC 425. It is preventive. It is, and here, when you migrate or you push data out of OpenPHA into here, it will tell you that in your HAZOP and LOPA, did you credit it as a PHA safeguard? Did you credit it as a LOPA safeguard? Selected SIL target, we know that it's SIL 2 with a PFD of 0.01. We can even put in things like required response time. Again, these things are kind of spilling out of that OpenPHA tool. Let's go ahead and leave it as Connexus Blue and hit update. So now you see this safeguard is going to protect against a feed composition change. I can expand and look at this in more detail. I can click the button and go back and edit the functionality. Now, let's look at some frequency numbers. So for this leg down here, feed composition change, you will see that a runaway reaction due to a feed composition change is now going to happen not once per year, but once in 100 years. And if you're familiar with LOPA math, we're just doing a probability multiplication where we take the frequency of the initiating event and multiply it by the PFD of the preventive protection layers to get a frequency of 1 times 10 to the minus 3 for this initiating event. And this number here, this frequency that sits underneath the top event, tells me how often the top event is going to occur. How do we do that? Probability addition. A runaway reaction will occur either because a feed pump failure at 1e-1 or a feed composition change at 1e-2. Add those two things together and you get 1.1e-1. That tells you how often you're going to get that loss of containment event. Once again, we've reduced our frequencies, but we're still not as low as we need to be to green light anything. So let me go ahead and expand a little bit. Now, looking at this high temperature reactor shutdown, this high temperature reactor shutdown is also going to be a preventive barrier to the feed pump failure. So I can click here, add a new safeguard, but in this case, I'm going to link existing so I don't have multiple copies in my database. I click link existing and say I want my TZC high reactor temperature shutdown, add a link, and boom, now you see that this is here in all its glory. It is the same database entry. It's not like I made a copy. So if I go in here and I edit, and instead of reactor, I just say RX, and I hit update, you'll see that it updated in both places. So it is a single, that single piece of equipment is a single entry in our database. All right. So now we've got this safeguard, and lo and behold, if I look, you'll see that this consequence, the safety consequence of other consequence, is greenlit. Why is that the case? Well, that's the case because this consequence is happening at 1.1e-2. The TMEL for this type of consequence is 1e-1. So tolerable risk is achieved for safety for other consequence, but the environmental for other consequence is not achieved because it's still red lit, and none of the runaway reaction stuff is tolerable still at this point in time. So let's keep drilling down and get into a little bit more detail. So another safeguard that might be available might be operator intervention based on alarm. So I'm going to click here and say add new, and I'm going to say TAH 175, and this would be reactor bed temperature for reactor 1. Safeguard type here is going to be an alarm, and my tag again is TAH 175 for operator intervention based on alarm. We're going to put that at 0.1 is what we typically do, and I'm going to hit update, and there you go. You can expand or contract to get more details, and you can see now how this frequency keeps dropping down. So the frequency related to feed pump failure is going to be 1e-4, whereas the frequency associated with the composition change is still 1e-2. Well, I think that high temperature alarm is going to be applicable to a feed composition change, so I can go ahead and add that alarm as a safeguard for this scenario also. And let's go ahead and, in order to make this a little bit more viewable, let's kind of minimize that and kind of hide the items. So now we've dropped down to 1e-4 here, 1e-3, and I still have a lot of red light over here. Now, let's go ahead and put in some mitigative barriers. So mitigative barriers are things that are effective after the loss of containment. So one thing I'm going to put in as a mitigative barrier, I'm going to add a new one and say I'm going to use a fancy name of occupancy control is my mitigative barrier, and then description would be procedures which limit the occupancy of the reactor area when the hydrocracker is in operation, and the safeguard type would be administrative control, and there is no instrument tag. It's not preventive because it's a consequence mitigation. Think about that. Now, if you've used occupancy or lack of occupancy in a LOPA, you've really never given any thought to whether that's preventive or mitigative. It's really mitigative because it doesn't prevent the runaway reaction from happening. It reduces the harm after it actually happens. But it is basically 100% effective. So I'm going to say that I only have a 10% chance of someone actually being out in the field when the event occurs. I'm going to hit update here. And now you see I have this occupancy control as a mitigative safeguard. Now, let's look at some numbers. So I already mentioned how we calculate the frequency of the top event based on an individual cause. So this 1E-4 is going to be the frequency of the initiating event multiplied by the PFD of the protection layers gives me the frequency of the top event or loss of containment as a result of feed pump failure. That's 1E-4. I did the same thing with feed composition change. It's 1E-3. So all of the causes of loss of containment, you add them together to get 1.1E-3. Now, this number here is going to be the frequency at which this consequence happens. So in order to get to this consequence, I need to get a loss of containment at 1.1E-3, but I also need for my occupancy control to fail at a 0.1 probability. So now what you're going to do is you're going to take the loss of containment, the top event frequency, and multiply it by the probability of failure of all of your mitigative safeguards to tell you the frequency at which this consequence is going to occur. So 1.1E-3 multiplied by 1E-1 gives me a frequency of 1.1E-4. So what have we done? Now you'll see that the environmental consequence associated with a runaway reaction, we're greenlit because the environmental consequence is tolerable at 1E-3, we're at 1E-4. But the safety consequence is red lit. It is still not tolerable. So let's continue and do a little bit more work here. Number one, I can add a safeguard. So you see right here when I hover over this plus button, it allows me to add a safeguard to a consequence. So I'm going to add the safeguard and I'm going to link an existing because that let's say that occupancy is going to be effective for the other consequence too. So occupancy control, add the link, and there we go. So now we're completely greenlit for other consequence based on that occupancy control. We still have this one red light, so our scenario is not done for this runaway reaction. We need to add one more protection layer. Do I have any other protection layers? Well, let me add another safeguard to this feed composition change. And I'm going to add another safeguard that says, I'm going to call it lab analysis. And lab analysis of crude for new batch should detect high concentration of olefins and cause operations team to reduce reaction severity. Okay, this is going to be operator intervention again. operator intervention. No instrument tag. This is, we'll put an NA there. And no SIL. The probability of failure, let's go ahead and give it that 0.1 that we would typically do. And now, kind of expanding out that significantly reduced the frequency of the feed composition change. But it's not enough. So I need to get to 1E-5 to make this risk tolerable. I'm sitting at 2E-5. So tell you what, why don't I bump up the SIL target of my safety instrumented function? So instead of a SIL2 with a probability of failure of 0.01 or a risk reduction factor of 0.01, I'm going to give it a risk reduction factor of 500. That would be 0.0002. Or that'd be 0.005. That would be it. Whatever. I'm not going to do the math in my head. I'm going to give it a PFD of 0.005, which is going to be a solid SIL2 instead of a borderline SIL2. When I do this, lo and behold, I have achieved my frequency. Now everything here on the right-hand side is green lit, and I am done with the design phase. So you'll see that this, you can replace everything that you're doing in LOPA in here, and it's a lot more sophisticated because you're looking at multiple consequences at the same time. Now, once you get past the design phase, you can do additional stuff in terms of those degradation mechanisms and degradation controls. So if I click here, now I'm going to expand my view of the safeguard to show the degradation factors and degradation controls. So a degradation factor could be operator not trained. Of operator training in response to the alarm. And I can hit update there. Another degradation factor. So once you open up, you click here to add more degradation factors. So another degradation factor would be alarm equipment fails to operate. So alarm equipment, including sensor and annunciation system fail to respond. So here, I mean, what you're seeing here is that I'm kind of going through and developing a list of failure modes of this safeguard. Okay, so when I do this, I can list out all the failure modes, and then I could put in my degradation controls. So here I can say operator qualification. And then I could say operator qualification requires the operator to be trained, tested, and certified prior to assignment to a board operator task. Training includes the alarm manual, which includes this alarm. Boom. So that is an example of a control. And I could do a similar thing for alarm equipment. I could put in testing program and say that alarm equipment is tested at each turn around. So that's my degradation control. So you could see that there's a whole lot of information here that can be shown to you for each safeguard, but normally while I'm working with it, I can just hit the hide button and all that stuff goes away. Now, another neat trick is all that information is also available wherever you view it. So this temperature alarm shows up for the feed composition change initiating event and the feed pump failure initiating event, and you can view it in either location or both location. And again, making a change up here changes it down here, because under the hood you're looking at a relational database. So a lot of power here. Couple of other quick things before I open up to questions. If I want to move things around, so if I want to move this interlock to last because it's going to activate last, I hit that button and I can move things back and forth. So let's make TZC 425 at the end, but I want lab analysis to be first because it's the first thing to happen. And maybe I want feed composition to be at the top, or no, maybe I want feed pump failure to be at the top. You can move things around to your heart's content. And then ultimately, if I want to report, I hit save the fault tree as an image. It's going to export as a PNG file. Now I have this Bowtie diagram, which I can import, export into anything else that I want. All right, so that is the quick and dirty brief overview of the Bowtie-Q software. Bowtie-Q software is now available from Conexus. We have launched the product. It is available today. And one important thing that I have not told you yet, unlike other people, Conexus is very proud of our pricing. So you don't need to, let me add a new page here. You don't need to go to our website. You don't need to beg for a price. You don't need to have one of our salespeople up in your business asking you a bunch of questions to get a price. The price is $3,500 per year for a single license. A single license is a concurrent user license. So that means when you have a license to Bowtie-Q, and I should be very careful, this is 2025 pricing. If somebody watches a recording of this webinar next year or thereafter, the price will probably have changed. But that's a concurrent user, meaning everyone in your organization has access to be able to use the software, but only one person is going to be able to use that software at any particular time. So we will get this up on our website shortly now that we're launched. You're going to be able to go eventually to store.conexus.com to buy it. So if I, why is this up here? I go to store, many of you might not know this, you could go to store.conexus.com and just buy our software. So if you wanted to buy OpenPHA, you click here, add it to your cart, hit checkout, and put in your credit. It already knows my credit card, so I could go ahead and buy this software directly from our website. It even knows what taxes I need to pay. Kind of some scary stuff. Bowtie-Q is going to be available in this format to where you're going to be able to go online, just buy it directly, removing all of that friction and preventing you, if you don't want to, from having to talk to a salesman. So with that, I'm going to come back here, and now I'm just going to go ahead and open the floor for any questions that anyone has. So let's begin, Chris, by letting me know, did anybody drop any questions in the chat?
Don't see anything in the chat. Does anybody have anything they want to bring up?
Well, that's kind of my objective here. I mean, with Conexus software, it's obvious. It's easy to use. There's no need to ask any questions because everything is intuitive and obvious. You just get into it and you go and you start working. Bye, everyone.